In this session, we have three exciting talks. First by Professor Farhan J. Ahmed, second talk by Professor Tokir Ahmed, and the last and the third talk by Dr. Kuntal Manna. So without further ado, let me first of all introduce to you all our today's chairpersons. Professor Brajendra Kumar Singh joined the Department of Chemistry as an assistant professor way back in 2010, and now he is a full-fledged professor. And he runs a very well-funded lab funded by DU, DST, DRDO, etc., that focuses on biocatalysis and metal catalysis, specifically in the design, synthesis, and evaluation of bioactive compounds. His exemplary research is evidenced by the numerous publications and presentations that he has so far given us. Professor Ramendra Pratap Singh, also a part of Department of Chemistry, DU since 2010, is a recipient of prestigious Alexander von Humboldt Fellowship. He has published more than 100 research papers, funded by DST, SERB, CSIR, ICMR, etc. His research is on the synthesis of various carbocycles and heterocycles, metal catalyzed carbon-carbon and carbon-nitrogen bond formation reactions, nucleoside modification reactions, and medicinal chemistry. So without much delay, I would request the chairpersons to kindly get on with the session. Thank you.
Good afternoon, everyone. So, as we know, our session is getting late, so I will first request all the three speakers of the session to deliver the talk within stipulated time, so that we can somehow manage the delay. So, in this session, the first speaker would be Professor Farhan J. Ahmed. He is he's in Jamia Hamdard and has 30 years of experience in teaching and research. He has several grants from DBT, IUS, UGC, DEST, almost of 5.5 crores, and he got 450 publication, 12 book chapters, 11 books, and has a US patent, 3 PCTs, and 24 Indian patents. He has a citation of 14,300, H index of 60, and I index of 257. So it's clearly saying his quality of work and dedication to the science. He has already supervised 43 students, and he has been awarded several awards from different agency, like 2005. In year 2005, he got
Short of time.
okay. Okay, so I mean there is many more thing which is here. So it will certainly take a lot of time to read all this. So with this short introduction, will request Professor Ahmed to start the talk.
Very good afternoon to all the respected audience, colleagues. Uh, the first talk after a very delicious lunch. I think it is one of the most difficult thing to deliver. And I'm extremely thankful to our experts for a generous introduction. I think this is too high for me. I will come here. Okay. Call him like this. Up and down transfer. हाँ डाल दो नहीं डाल आवाज आनी चाहिए बस can you hear me okay so today I just want to give an introduction about advanced regulatory system. As we all know, any API or active pharmaceutical ingredient or drug has to be delivered to a patient in a proper platform. So we can achieve a proper therapeutic potential from that drug. Drug per se, when they are synthesized, they have some specific physicochemical properties, and these physical properties can be they are about their solubility, about their pharmacokinetic, about their chemical properties, about their stability. A formulation scientist or a drug delivery scientist has to read all those properties and design a platform by which, when it is given to the patient, it should reach the site of action in the desired concentration. In normal drug delivery systems, like which are immediate release, like we have tablets, capsules, suspensions, they are mainly used for those drugs which are freely soluble, easily absorbed by oral route, which is the most widely used route. But when we have difficult drugs which have very, very poor solubility, poor stability, poor pharmacokinetic, then we have to design some advanced system where we can improve those properties and achieve the maximum potential and best safety from those drugs. So this is about those advanced systems. Just to increase the interest of the students in these systems, I've also taken literature from the market. What is the market potential of these systems? Now, a targeted delivery system which basically, specifically and preferentially deliver the drug to the site of action. Whenever we take a drug by oral route, it absorbs from our GIT, goes to the circulation, and from circulation it reaches the whole body. So our whole body is exposed. This is very good for those drugs where we want immediate action, like analgesics, antipyretics. But if you are talking about a drug which is toxic, like anti-cancer drugs, or drug which you want to only affect the brain or only liver, then in those cases we don't want to expose the whole body, because that invites undesirable side effects. So targeted system is something which is a magic bullet, which is coined by the term Paul Ehrlich, and where we can at least preferentially target the affected organs. Maybe not 100% goes to the organ, but maximum amount will goes to the desired organ, and other organs I'll be spared. So this is a brief history which I have taken from the literature. If you see, in 1950s, it was so old when the first special system was designed, that was expansules. We have all used free-fall capsules. They are also type of expansules, where there we have coated beads, and those beads, they release the drug or iron slowly in the body, so it can be absorbed and for a prolonged period of time, and we get the good amount of iron in our bloodstream. Similarly, we have accusers. In 1964, liposomes were launched, which are lipid system, with the name of bangosomes. In 1974, accusers, which are supposed to be placed in the ocular cavity and release the drug in the ophthalmic cavity. Then in 1975, osmotic systems, which can deliver the drug under the osmotic pressure, where we can control the release. Then we have, in 1974, iron dextran complex, very good form of iron which can be absorbed. Then in 1975, transdermal systems were introduced, which were supposed to be applied on skin, and through skin the drugs are being absorbed. Then we have like system like 1995 doxil, pygylated liposomes, pygylated proteins. This is the era of pygylation, where we can pygylate the system, inject in the body, and because of pygylation they become hydrophilic and they can circulate for a longer period of time in the blood circulation. They can avoid our RES system and they become acceptable. Then we have the era of nanomedicine, where we have a lot of nanoparticles, nano herbals, which are being used for anti-cancer treatment or targeting system. And there are other examples, Norplant, which is used for fertility control, then Repamune, nanocrystals, which are not having any polymer or system, only crystallized particles. Then we have the era of proteins and peptides, which cannot be given by oral route, which has to be given by route other than oral route, because they are digested in our GIT or in our small intestine. Then we have Taxols, popular anti-cancer drugs. Then we have Apatro, then we have Camera, Combinati. They are all the advanced system in which are starting from 1950. This is the long history. Now, if you look at the market potential, the global market is about more than 6,000 million US dollars in the year 2022, and it is growing at a compound annual growth rate of about 15 to 9%, which shows a very promising area for the students who want to select their area of research and where you have the potential, because companies are now looking forward to these systems, and if you have a specialization or expertise in these systems, obviously your acceptability by a company, your placement will be improved. If you see, the most market is covered by oncological disorders, cardiovascular diseases, then endocrine system, and this is the markets which are more having the more market share. So the driver to these markets are basically because nowadays more and more incidence of chronic diseases like cancer, cardiovascular, lifestyle diseases, respiratory disorder, especially after COVID. Now we are more concerned about our health. We also have a fear of those unknown diseases which may come in the future. Either they are communicable or non-communicable, or because of our lifestyle. Then another area reason, the technological advancement which is taking place in the area of drug delivery system. Why it is happening? If you see in the last 20 or 15 years, the new chemical entities are number of new chemical are being launched. It is becoming rare because the cost of development is more than $600 billion or $500 billion, while developing a new formulation is only $100 to $200 billion. In a new chemical entity, the success rate is very poor. Out of 1,000 molecules, only few molecules will see the day of light. They will be approved by US FDA. Your company will launch them in the market. But if anything happens in the post-marketing surveillance, any undesirable effects comes out, then you have to withdraw. Like Copsibs. What happens is with Silicopsib, the main problem, they invest all the amount of money, it was launched, and but after 10 years or 5 years, because of those effects which appear in the post-marketing surveillance, they have to withdraw. So success rate is very low. While in case of new formulation, you will get the patent, you will get the extension of patent, and your success is 100% guaranteed. Then rising investment in the companies who are producing biotechnology products. There are the two examples. I will not go into details. Then in COVID also has a very good factor where companies are focusing on new molecules and new chemical entities. Now, to develop a new formulation, you always have to approach a multidisciplinary approach. You cannot work in silos. You can not work in only your lab because you cannot be master of every art or every science. You have to collaborate with a clinician, with a biological person, with a chemistry person, especially material scientist, engineer, and then you can definitely you can reduce the time which is required to develop a molecule. Because if you want to do yourself everything, then I think your invention will never see the day of light. So it has to be a collaborative work, multidisciplinary approach, where you can collaborate with hospitals, with doctors, with scientists, with chemists, and then come out with a product. So these are the systems which we are using for proteins, peptides, carrier-based, transdermal, mucoadhesive, drug devices. These are the carrier-based systems which are liposomes, nuosomes, uh, lipospheres, microspheres, solid particles, nanostructure particles, microemulsion, and so on. Huge types of systems are available for various applications. And this is the example of other PGlated proteins and peptides which are launched in the market starting from 1990 to 2020, and they are already available in the market. Now, if you look at the transdermal system which were launched in 1960s, initially only scopolamine or some anti-hypertensive drugs were available in the US market. But because of the technical requirement, you have a separate manufacturing equipment. A company which is situated in India, where they cannot invest into a new manufacturing facility, nobody was interested in purchasing a new machine to make a transdermal patch. It cannot be made on a tablet machine. It cannot be made on a capsule machine. So they have to invest. So because of this, initially there was a downtrend in the market, but now it is again picking up. If you see in the compound annual growth is about 4 to 5%, and it is reported to be about $8 billion in 2028. So it is also a promising area. And the systems we have used for transdermal, we have hydrogel transdermal patches, insulin patches with microneedles, which can be applied on the dermis. The microneedle can penetrate your dermis and can deliver the drug at a controlled insulin at a controlled rate. Then we have matrix systems, reservoir systems, drug and adhesives, and multi-laminate systems. So they are all available in the market. We have sonophoresis, where we can use sonic waves. We can use laser assisted lead system, which can be used. Then another area is mucoadhesive system, which are applied on the mucoadhesive surfaces. It can be buccal mucoadhesive surface, it can be sublingual, it can be vaginal, it can be rectal, it can be oral. So mucoadhesive system basically increases the residence time of a system on the area or surface where it is applied. When we apply in the buccal cavity, it can stay there from 6 to 8 hours, because a loose system will not stay by the actions of chewing or swallowing. It can be dislocated. So we have variety of systems which are used for mucoadhesive. We have ocular route in the ocular cavity. We can have mucoadhesive nanoparticles or microparticles which can stay there on the surface of the retina. Then we have nasal route, because nasal route is also used for brain delivery. You can have mucoadhesive particles which can stay inside the nasal cavity, and from there on the drug can be absorbed. Then you have buccal route, which is already used for various applications. Oral route, where we can take orally, and if it is adhered to the our gut surface, it can stay there longer than the gastric time, which is about 2 to 3 hours. It can stay there for 6 to 8 hours. Then we have vaginal route. There also we use mucoadhesive system, and the polymers which we are using are alginate, pectin, xanthan gum, arabic gum, carrageenan, hyaluronic acid. They have very good mucoadhesive property. They form bonds with the mucous surface and then they apply. So this market is also growing at about compound annual rate of about 9.2%, and this is also companies are taking interest. These are the examples: buccal, or you can say nasal. Then we have systems, ocular systems, and vaginal systems. This is another type of advanced regulatory system where we use a osmotic or a salt. When salt is coated or it is applied inside the tablet, and with a laser drilled aperture or through a semi-permeable membrane, the drug can be released from this aperture or from the membrane. Push and pull system, drug is released, pushed out at a controlled rate, and you can control the release of drug, and it can be given orally. This is the market in the US market, about 47 US billion dollars, and this is also growing at a very good about 10.5% compound annual growth rate. These are the commercially available oral osmotic systems: Nifedec, which contains nifedipine; then Alpress with prazosin, which is used for hypertension; Bribamil. Then you have cold medication pseudoephedrine available at the name of Efidec, glyphosate. The purpose of giving example is that these are not myth, or these are not only stories. These systems are already being developed, gone through the critical phases, and they are in the market. So these are successful. These are the implantable osmotic pumps which can be implanted as a depot system. They can release the drug for weeks. So for prolonged release, where you want like drugs like anti-epileptic drug, where patient cannot or maybe forgetful, a person is suffering from depression or schizophrenia, or he's suffering from Alzheimer, Parkinson's disease. So those patients, they are forgetful. They cannot take the medication on regular. So their osmotic pumps as a depot systems are very successful. Then we have stent market, where you have drug coated stents, which are drug eluting, which can prevent the deposition of fats and lipids onto the surface of the stent, which is implanted in your artery, and they prevent the clotting. The market is huge. You know, we are all have a increased incidence of cardiovascular diseases, maybe because of one or the other reason, but implants are inevitable if you have a blockade and you have to use that, and they are very costly. The market is huge. You can see it is about 5,000 billion US dollars, and it is we have covered stent, we have bare metal stent, and we have bioresorbable stent, which can be degrade naturally and reabsorbs. Then we have micro stents which are used in glaucoma. In glaucoma, you have a blockade where your fluid is not being pushed out or pumped out from your ophthalmic cavity, so you can use a stent here. Then this is another area where you have hormone releasing intrauterine devices for family control. You have now plant, you have intrauterine devices, and this market is also growing at a very good growth rate. Compound annual growth, you can see more than 3%, more than 6%. And these are microchips, which where you can program the drug release at a given time during your disease condition. If you are hospitalized, these microchips can be controlled from outside, can be implanted under your dermis or skin, and you can control the release. You can see the global market of the connected drug delivery devices. It is about in 314 billion. About growth rate is about 35%, and this is a huge potential. The area you can choose for research. The diabetes mellitus is also, we are also a nation of diabetes, where we have, because of lifestyle and our food habits, this is developing, and this market is also growing at a huge compound annual growth rate, and they're about 28.54 billion by 2029. This is the insulin delivery market. We have insulin pen, which are used for delivery. We have home care segment, we have hospital and clinic segment, and global. This is the global statistics. The compound annual growth is about 7 to 8%. And if you see the share of the various devices, insulin pumps, insulin pens, insulin needles, jet injections, these are the pens which are more commonly used. These are the jets where we inject the drug by a pressurized air, and then we have pumps where we can control the delivery of insulin. They have glucose sensor. They can release the amount of increasing glucose, and then they can release the insulin. These are inhalers, although they are not very successful clinically because of the patient-to-patient variation, but they are also in the market. And in nanomedicine market is also growing. We are daily we are having huge amount of products which are being approved by US FDA. Just to show you, these are the drugs which are already approved and are available in the market, and they are based on nanotechnology. You can see you have Horizon, you have Peligri, you have Adipinomate. They contains drug for multiple sclerosis, chronic gout, hemophilia, osteoarthritis, control and prevention of bleeding episodes, and prevention of bleeding in the preoperative setting. These are the Abraxane, which is used for cancer, breast cancer. You have Sistina, Janssen Pharma, which is used for schizophrenia. Then you have all these examples. They're already in the market and they are being used. Then we have drugs in the form of proteins and peptides, which cannot be given by overload because of their sensitivity. This market is also have a compound annual growth about 8.7%, and it is in 27. It is the future forecast is about 15.24 billion US dollars. Other area is implants, which are injected into the under skin. You have different types of implants. Orthopedic implant market, which is nowadays increasing. They are also drug coated and drug eluting. Then you have global ocular implant market. You have facial implants, and you have dental implants. They are all available in the market. These are marketed product example. You can see they are all depot formulation. They are not oral or they are not tablet or capsule. They are all depot. Vivitrol, Signifor, Lutrate, with different technologies. So there are already companies are investing and they are developing these products. So if you choose these areas for our research, our expertise, our knowledge will help us in getting good placements and good jobs. This is one of the work which we have done about 15 years back. And this is one product which we have developed for defense with Inmas DRDO. And this is we have developed respirable nanocyte particles by controlling their density and particle size. Because in the literature, what we found that particles which are available in the market as a dry powder inhaler, when a patient is inhaling those DPIs, the average lung deposition is about around 30 to 40%. The rest of the drug either goes to trachea or go to GIT or it is inhaled out. Then we try to develop the particles and modify its density and particle size, and we could achieve a deposition about 6 to 80%. So this you can see when particles are tagged with technetium 99, after 15 minutes, the lung fields are much more brighter and here as compared to the micron size particles. And the most surprisingly, after 6 hours, the drug was still there, while in micron particles there was no drug. So it was acting as a depot. So by looking at that technology defense, immediately they have a serious problem of COPD, chronic obstructive pulmonary disease, in the armed forces who are deputed at high altitude in Leh and Ladakh. There, because of oxygen and pressure condition, they develop COPD. And COPD is a disease in which if a person is sleeping and oxygen level goes down, he can become unconscious and he will die. And there is no hospital in those very severe conditions. You have to bring him back to the base hospital, or you have to give a subcutaneous injection. But when you are covered from every angle, giving injection, you need a trained person. And secondly, it is not an emergency way of giving the medication. So we developed DPIs. You can keep in the pocket. Even if you are a high altitude, you can just take a single puff. And what we found, when you're taking single puff in patients of proven pulmonary hypertension, the pulmonary artery pressure is reduced by 25%. Oxygen content is increased by 10%. Heart rate is reduced by 8%. And exercise capacity is increased by 33%. So this can save their lives. They will get about golden time of about 6 to 8 hours. and their oxygen content is increasing, exercise capacity is increasing, so they can be easily bring back to the hospital in the base areas, in the base location, and they can be treated. So this is already, we have gone through phase 1, phase 2, phase 3 clinical trial. It is already adopted by defense personnel. So this is one success story which I want to share with the students. And the future is very promising. More and products are developing into advanced delivery systems. One reason is to achieve the excuse me, to achieve the better therapeutic outcome. These systems are being designed. Another reason why companies are doing it, they want to have a better protection with respect to patent. They get the extension of patent if they can develop a system where they can show that there is a significant improvement with the previous technology. When we are comparing with the previous technology, they will get the extension of patent life, so they can capture the market in those extension of patent time, and definitely they are getting benefit with this investment. So this is the area where students can work. Then conditions like COVID-19, this is also has highlighted the importance of developing a system which can protect us, which can treat us in those special conditions. These are a few images of Jamia Hamdard. I think many of you might have seen my research group. Thank you.
Thank you for completing the lecture on time. So if there is any question, any doubt, any suggestion, the session is open for discussion. If no, then I must say thank you, sir. Please.
I just try to finish it fast.
Yeah.
So at least
Yes. So the next speaker of this session is
Sir,
Professor.
I would like to request you to kindly felicitate our speaker with a memento now. In between, after. If you say we can do it at the end, together at the end. Okay. Okay.
So the after that, after all three. So the next speaker of this session is Professor Tawkir Ahmed, and he did his graduation from IIT Kanpur and PhD from IIT Delhi. Presently working as a professor at Department of Chemistry, Jamia Millia Islamia University. He has already supervised 14 PhD students, 77 postgraduate, 9 projects, published 158 research publication, 1 patent, 2 books, H index of 45, I10 index 130. So he has already reviewed at least 137 journals. They deliver 134 invited talks, presented 128 invited lectures at different conferences. He has been a recipient of award from DST, SMC Bronze Medal Award, ISCAS Medal Award, and for his academic teaching, he has been awarded Inspired Teacher President Award, Distinguished Scientist Award, Maulana Abul Kalam Azad Excellent Award of Education, Teachers Excellence Award, and many more things are there in his list. So I will request Professor Talk to initiate his talk.
Yeah. Thank you, Chairman, for the nice and the detailed introduction. I must thank all the organizers, especially Dr. Pratibha, for inviting me in this prestigious conference. And good afternoon to all of you. So the title of my presentation is the hydrogen generation through overall water splitting using functional heterostructure, which is the actually global demand in a present scenario. So actually when we talk about the functional materials or the nanomaterials, so this is a very basic slides meant for the students. Basically nanomaterials are very fine materials having grain size in the range of 1 to 100 nanometers, and as you know the typical size of any atom is 1 to 2 angstrom. Therefore in 1 nanometer you can arrange 5 to 10 atoms. So at this nanometric dimension, the material shows some unusual properties because of the number of reasons, like the confinement of electrons. They will have high uh, surface to volume ratio of atoms, and the electric and magnetic dipoles are highly disordered at the surface. So because of these unusual properties, the nanomaterials could find applications in a very wide areas, like in the electronic devices, memory devices, catalysis, sensors and energy. And today I am going to speak about the catalysis and the energy part. But when you talk about the actually nanostructures, basically nanostructures can be defined if one of the dimension of these materials is in the nano range. So these nanostructures may be of nanoparticles, maybe of like nanorods, nanoneedles. These are bipods, tripods, tetrapods, nanocylinders, nanoflowers. Many actually shapes you could see actually in the literature, as well as when you do actually implement these in research. These are actually nanowires. This is the core shell nanostructure. These are the nanotubes. So these are the various actually structures. So when you actually see the different objects or the different materials, then you can see actually when you reduce the size of the objects, what happens actually, the new surfaces are actually increasing. So the surface energy will increase, or the surface area for a constant volume, this will increase. So this is the actually typical representation how the surface area will increase when we reduce the size of the objects into the nano dimension. Now coming to the nanocatalysis, actually when we do nanocatalysis, so we can do actually these kind of reaction many ways, like the organocatalysis, like Dr. Manna is there, Dr. Venka is there. They are also doing like homogeneous, heterogeneous catalysis. So organocatalysis, then photocatalysis, electrocatalysis, photoelectrocatalysis. So the basic objective of uh, organic transformation actually is to produce the medicinal products which are actually industrially viable, and this is the actually general mechanism of any type of the catalysis. The general mechanism of any catalysis involves the three steps. In the first step, actually the catalyst give its surface to the reaction media, mean the absorption of the reactants over the surface of the catalyst, where they can actually energize and make a chemical reaction. So during the chemical reaction, there is a rearrangement of the actually chemical bonds. Some bonds are broken, some bonds are formed, and in the final or third step, the reactant molecules are dissolved and to convert into the final product. So this is actually one of the part that actually we are doing in my research lab actually in the organocatalysis. So we have designed several nanostructures, pure metal oxides and very beautiful metal doped metal oxides, and we have actually used these metal oxides for the many organic transformation reactions involving hydrogenation, carbon-carbon coupling, amination, oxidation and electrophilic cyclization. But today actually I will speak on actually another part, which is the photoelectro and photoelectrocatalysis, means water splitting. So basically water splitting, actually this is a simple approach. Probably Professor Venkata maybe yesterday speak over on this area, because he is also expert of these kind of the reactions. So basically water splitting is a simple chemical reaction where you actually break the water molecule into the elemental hydrogen and elemental uh, oxygen. So actually this reaction looks very simple, but this is not as simple as you can see on the board. Actually this reaction requires some driving force, and the driving force for these particular reactions are the presence of the catalyst or some light actually, and the simple light source is the sunlight. So if you study the solar spectrum of the sunlight, then you could see actually the maximum component of this light is the visible light. So in our life actually we need to design the functional or the advanced nanostructures which are actually visible light active. So to get actually visible light activity, actually you must actually know their actually optical band gap. So if the optical band gap is in the range of like 1.8 to 3.2 electron volt, then the material should be the visible light active. So to make these materials, you need to make some chemical modifications. So we do actually chemical modifications either by actually doping of element into the host crystal, or designing some heterostructure. So nowadays the maximum researchers actually are working in this area. They design actually the different kind of the heterojunctions or the heterostructures and apply those materials in a various kinds of the applications. So actually the concept of this kind of the chemical modification to tune the optical band gap into the actually visible region or whatever the region actually in which you are actually interested. So the main actually reason is that actually you need to enhance the photocatalytic activity of these materials and you need to reduce the electron hole pair recombination. And the second point is that actually these materials should have the small grain size and there must be the high surface area. So if small size is there, material will have the high surface area, means high uh, surface active sites will be there actually which are used to catalyze the chemical reaction. So why actually we are so much interested in green hydrogen or the hydrogen? So if you see uh, the actually energy crisis, you could see globally, and there are actually certain reasons actually for the causes of the energy crisis, like the overpopulation, poor infrastructure, overconsumption, lack of actually infrastructural facilities, and actually to store the energy. So the whole actually world actually is looking for the alternate source of energy, and actually the earth oil may be actually vanished very soon. There is a prediction it may have life of 40 years, 50 years, or 60 years. So we have to transform actually everything either on the renewable source of energy or the uh, yeah, so hydrogen actually is considered as the clean fuel and the green energy. This is carbon free and highly abundant, and this is environmental friendly and has zero impact on the environment. So basically, the overall water splitting, which is actually considered for the photocatalysis, electrocatalysis, and the photoelectrocatalysis. So these three phenomena are collectively called as the overall water splitting, and these methodology are considered as the most prominent methods for water splitting to produce the economical green hydrogen to resolve some of the energy crisis. So I will speak actually over these three methods and will show some of the results actually that we obtained actually in the research lab. So this is the actually mechanism and the experimental conditions to make the photochemical water splitting reaction. So to make this reaction actually you need to have the your nanocatalyst, which is your either the doped metal oxides or your heterojunctions or the heterostructures. So in the specific amount you need to take with the sacrificial agents. So several sacrificial agents are available, and add the required amount of the double distilled water, and actually any water you can take. Actually some researchers are working on the sea water also. We have also just now published a paper on the sea water splitting. So in a certain amount, if you take these solution in a specialized glass cell, and you need to evacuate and make the inert atmosphere by purging either argon or by nitrogen, and then expose with the light. And the wavelength of the light actually it depends on the actually optical band gap of your photocatalyst of your nanomaterial. So actually you need to actually use the different band pass filter, so that actually you can tune the wavelength of the light source. So and at the certain time actually you need you have to take actually the hydrogen by taking the spatial injection and inject over the GC machine. Then if hydrogen or any other gas is there, then actually it will give signal over the screen. So basically in this whole actually reaction, initially actually the light is absorbed by the photocatalyst, and it gives the holes in the valence band and the electrons in the conduction band, and you need to inhibit the electron hole pair recombination, and the electrons which are present over the conduction band, they are actually used to reduce H plus into the hydrogen gas. The second methodology is the electrocatalytic water splitting. So basically this method is the simplest method which is known for water splitting. So here actually you use the direct current for the separation of water into hydrogen and the oxygen. So basically the hydrogen evaluation reaction occur at cathode, and OER means oxygen evaluation reaction occur at anode. These are the half cell reactions. And here this is the electrochemical water splitting setup. Both actually methodology are same. The difference is that actually in another set of reaction we use the light source, and the second the Cell setup actually is different because actually you need to make the arrangement so that you can easily pass the light in this setup. So first actually we have prepared this material, the graphitic carbon nitride nanosheets, because actually graphitic carbon nitride we took for making the different heterostructures. The reason is that actually the GCN is an ideal candidate for photocatalytic water splitting due to excellent alignment of the band edges with water redox reaction, and the synthesis is also very simple. If you have you take the melamine, and if you actually heat at around 520 degrees centigrade temperature, you will get the bulk graphitic carbon nitride. And if you exfoliate this bulk graphitic carbon nitride in sulfuric acid or the HCl, you will have the very beautiful actually nanosheets of the graphitic carbon nitride, and these are the very beautiful actually electron microscopic image of this graphitic carbon nitride nanosheets. These are the Buffy like morphology, and if you have the understanding of the HRTM SEM, then you could see the tilting of actually sheets during exfoliation of the graphitic carbon nitride in this phenomena. So these are the primary investigations like the surface area and the optical band gap, because actually if you have the primary investigation, then you can directly go to this water splitting measurement. So for the water splitting measurements, we made the two different set of reaction. In one set of reaction, we take the sacrificial agent as sodium sulfide and the sodium sulfite, and in another set of reaction we take the trithenolamine as the sacrificial agent, and we perform the two different set of reactions simultaneously, and we observe that the trithenolamine can generate the high amount of the hydrogen, which is around 470 micromole per hour per gram, with an apparent quantum yield of 12%, whereas the sodium sulfide and the sodium sulfide can generate around 230 micromole per hour hydrogen with an apparent quantum yield of the 7%. Then these are the photo electrochemical activity towards HER reactions. So this is the HER plot and this is the OER plot. So low value of the onset potential can lead to the high photocurrent density, which actually requires the less voltage for the significant hydrogen generation. And this is the TEFL slope. Here actually you can see the low value of the uh, over potential, which shows the high or the significant HER reaction, and this is the turnover frequency plot, which is actually used to actually determine the intrinsic activity of the graphitic carbon nitride nanosheets. Then these as prepared graphitic carbon nitride nanosheets were used to design the heterostructures with the copper ferrite. So we have prepared the type 2 copper ferrite graphitic carbon nitride heterojunctions and apply for the photo and the electrocatalysis reactions. So the methodology was simple. Initially you prepare the graphitic carbon nitride as I have discussed earlier, and prepare copper ferrite by using simple hydrothermal method, and mechanically if you mix them in the different weight ratios like 10 weight percent, 20 and 30, we have taken three compositions, and then actually uh, study initially we do the primary characterizations like the BT surface area and the detailed U visible or the DRS study for the optical band gap, and if you have the good understanding of the X-ray diffraction, then actually you can easily index each and every reflection, and you can actually confirm that whether you will have the heterojunction formation of copper ferrite with the graphitic carbon nitride. And then these are the actually photochemical hydrogen generation. Again actually we made the two set of reactions, uh, one with the sodium sulfide and the sodium sulfide, which gives the lesser amount of the hydrogen, whereas the trithenolamine gives the high amount of the hydrogen, and here actually we obtained the maximum amount of the hydrogen production by using the 28% of the copper ferrite loading over the graphitic carbon nitride. This is because actually high loading of the copper ferrite over graphitic carbon nitride can likely reduce the light absorption by highly porous graphitic carbon nitride nanosheets, and therefore decrease the formation of the electron hole pair. And we also actually added the actually to get the actually high amount of the hydrogen by using trithenolamine. This is because actually the non-polar nature of both the catalyst as well as the sacrificial agent, it results the improved interaction and the wettability of the catalyst surface. These are the actually charge transfer dynamics which actually we study to actually see the electron hole pair structure, and band structure mechanism we have also explained over here. This is the impedance spectroscopy. the low circular charge semicircular ring refers for the low charge transfer resistance, and which leads to the enhanced interfacial charge transfer. And these are the Mott Schottky plots. This is for the graphite carbon nitride, and here it gives the positive Mott Schottky plots, which refers for the N type of the semiconductivity in graphite carbon nitride, and the negative Mott Schottky plots in copper ferrite refers for the P type of the semiconductivity. And when you have the hetero junctions, then you can see the positive and the negative Mott Schottky plots, which refers for the PN junction formation of these heterostructures. And this is the PL plot, and here you could see the decrease in the PL intensity, which suggests for the low recombination rate. And this is the band structure mechanism. Here it shows the band structure of the pure copper ferrite and the graphite carbon nitride before the heterojunction formation, and when actually the heterojunctions form, the Fermi level band alignment occur, and here the actually the electrons from the conduction band of the copper ferrite tunnel to the conduction band of the graphite carbon nitride, whereas the holes from the valence band of the graphite carbon nitride transfer or tunnel to the valence band of the uh, copper ferrite, and these electrons are used to actually reduce the H plus into the hydrogen gas. So this is the actually OER plot for copper ferrite graphite carbon nitride heterostructure, and the corresponding Teffel slope, and this is the HER and the corresponding Teffel slope. So these studies give the low onset potential and improved current density, which signifies for the high HER reactions. And we also obtained the high or the maximum Faradic efficiency for the 28% copper ferrite over graphite carbon nitride, which refers for the free electrons in the actually conduction band for making the significant photochemical reaction that we have discussed in the earlier slide. Then this is the copper oxide graphite carbon nitride heterostructure. So here actually we prepared the copper graphite carbon nitride by using the same methodology as we have discussed earlier, and the copper oxide by using simple uh, hydrothermal method, and then we have prepared the heterostructures of the copper oxide with graphite carbon nitride in three different ratios: 10 weight% loading of copper oxide over graphite carbon nitride, then 20 weight%, 30 weight%, and these are the actually basic investigations. Then uh, this is the actually theoretical investigations. Actually here actually if you see the structural information of graphite carbon nitride and the copper oxide, they have the different structure. So first actually we do the produce the structural similarity, so that actually when we do actually this study, then the study model shows that during the formation of the heterostructures, the conduction band become more populated, which is actually helpful for our study. Here actually if you see the detailed investigation for the hydrogen evaluation, then you can see the 38% loading of the copper oxide over graphite carbon nitride can produce 3.5 millimole per gram per hour per gram hydrogen, and the apparent quantum yield actually is increased from 10 to 18% for the 38% copper oxide over graphite carbon nitride. So this is the actually first report which actually reports the highest apparent quantum yield for this binary heterostructure, means copper oxide and the graphite carbon nitride. Then these are the actually HER and the OER reaction. So both these investigations actually shows that actually this gives a very impressive electrocatalytic results, and we have shown that on the basis of our results that these as prepared binary heterostructures could be the best replacement, as we do have the commercially available iridium oxide. Actually our results were quite comparable for the iridium oxide. This is the heterostructures of the cadmium selenide quantum dots with graphite carbon nitride, and this paper is under consideration. Actually, in fact, actually we have submitted the revision part in ACS catalysis. So we have prepared these CDSC quantum dots by using SILA method, and we actually apply the 10, 20, and the 30 SILA cycles for the formation of the CDSC quantum dots, and then mix with the graphite carbon nitride, and actually these are the primary investigations. Now coming to the main part, this is the actually detailed electron microscopic investigations, and if you see the high resolution transmission electron microscopy, then the different lattice fringes could be seen, one actually corresponding to the graphite carbon nitride and another for the CDSC quantum dots. And we have matched these actually lattice fringes with our lattice interplane distance of the by using the X-ray diffraction. And here the hydrogen evaluation could be seen actually, a very high amount of the hydrogen could be obtained, which is around 4.4 millimole per hour per gram with an apparent quantum yield of 23.8%. And these are the electrochemical investigations, and here actually 38% 30 cycles of CDSC quantum dots over graphite carbon nitride heterostructures could actually give the significant HER reaction. Now coming to this ternary heterostructure, so these are the ternary heterostructures that we have prepared for molybdenum sulfide boron nitride with TiO2. And these are the X-ray diffraction investigation. These are the detailed actually electron microscopic studies for the binary and the ternary heterostructures of the MOS2 boron nitride and the TiO2. And these are the DFT studies which shows that the structure of MOS2 and boron nitride actually was similar, as well as the band gap with the as observed by using the X-ray diffraction and the optical band gap studies. The structure of the TiO2 was actually same as we do have in the X-ray diffraction, but the optical band gap was underestimated due to the DF Coulombic interaction, and the similar band structure we also obtained. This paper is published in the International Journal of Hydrogen Energy. So we do the photochemical hydrogen evaluation for these ternary heterostructures, not ternary actually. We applied for the monophasic, binary and the ternary, and these ternary phases actually we prepared for the 2.5 weight% loading of MOS2 boron nitride over TiO2, then 5 weight% MOS2 BN over TiO2, then 7.5, and this 2.5 MBT could actually give the significant result of the hydrogen production, which was around 2.7 micromole per gram per hour. And this is the actually XPS spectra, the peak shift on over the left hand side and the decrease in the PL intensity could lead to the lowering in the recombination of the photo generated charge carrier. And this is the band structure of the TiO2, and this is for the MOS2 boron nitride, means the binary heterostructure, and this is the band structure for the ternary phase of the MOS2 boron nitride, the boron nitride with TiO2. These are the electrochemical investigation, and it shows that the low onset potential and the low over potential of the 2.5 MBT, means 2.5% loading of MOS2 boron nitride over TiO2 can give the significant result. And if you see the chronoamperometric plot, then actually it shows that in a 4 hours time the HER reaction actually could become doubled in 4 hours time. This is the photoelectrochemical investigations, and it shows that the this 2.5 MBT could generate 7.5 milliampere per centimeter square high cathodic current, and this is the EIS plot, and the lower semicircular diameter of 2.5 MBT could actually lead to the accelerated interfacial charge transfer, and this is the transient photocurrent plot for 2.5 MBT, and it shows the stability up to the 6 consecutive cycles. And here this is the Mott-Schottky plot for which shows the proper band alignment in our as prepared 2.5 MBT. Now coming to the conclusion, we have obtained the adequate apparent quantum yield for of nearly 12% and high Faraday efficiency, which is around 99%, which makes graphite carbon nitride nanosheets as the prominent metal free semiconductors to produce hydrogen. And the 28% copper ferrite over graphite carbon nitride heterostructures could produce hydrogen of around 970 micromole per hour per gram with an apparent quantum yield of 25% and high Faraday efficiency of 94%, makes it a potential candidate for efficient hydrogen generation. And this copper oxide graphitic carbon nitride heterostructures could generate a very high amount of the hydrogen with an apparent quantum yield of 18%, and the impressive electrocatalytic performance could be observed. And this 2.5 MBT exhibit the optimum photocatalytic response with the production hydrogen production rate of 2.5 millimole per hour per gram with an apparent quantum yield of nearly 7%, and the 30 cycle CDSC quantum dots over graphitic carbon nitride heterostructures showed high photocatalytic hydrogen production of around 4.3 micromole per hour per gram with an apparent quantum yield of 24%. So now to conclude, I must actually thank my research group. These are my past and they are my present PhD scholars. I must thank my collaborators, Professor Chari, Professor Banerjee, Professor Mao, Professor Ahmed, Professor Samir Sapra and Ingole. They are from IIT Delhi. And I must thank the funding agencies, DST, SERB, CSIR, Spark, and of course Jamia. And I must thank you for your patient listening. Thank you very much.
So thank you, Professor Taqir Ahmed. If there is any question from audience,
Yeah.
please go ahead.
A very nice talk, Professor Ahmed.
Thank
So
you.
my question is, in one of your slides where copper ferrite with the graphitic carbon nitride in the recyclability data. So until 3 hour, the hydrogen evolution is increasing, but at the 4th hour, it again tends to decrease a little bit. So
Yes.
in one of your beginning slides on copper ferrite with GCN.
Yeah, it is there in the copper ferrite with graphitic carbon nitride.
Graphitic carbon nitride,
Yes. Actually, this comment actually we obtained from the reviewer also.
Okay.
Yeah, I will show.
This one
Yeah, this one.
plot C.
Yeah, here, no.
No, plot C, the recyclability
This
data.
one.
In the first cycle, there is up to 3 hours it's increasing and again it's decreasing at 4th hour. Is it because of some saturation effect or what?
Yeah, some saturation effect as well as actually the loss of the sacrificial agent as the time passes.
Yes.
So
yes.
this is the case, and
Okay.
with the help of the PL and other investigations, we have actually responded for this query.
Okay, excellent. Thank you.
Okay.
Nice talk, sir.
Thank you.
Sir, I have some queries. Like you have shown that many of many of your results have shown good results of hydrogen
Hydrogen,
evolution.
yes.
So did you further move forward to use those hydrogen in some applications? Like did you capture?
Nowadays, we are actually doing these experiments at laboratory scale.
Acha.
Right? So that is our next step actually.
It's like it can be used further for
actually that is for the hydrogen storage. Actually,
application of hydrogen.
Yes. Hydrogen storage. Actually, when you do not have the setup for the hydrogen storage, then you could not actually apply for other industrial applications.
Because some of the
This is actually
good hydrogen
for
evolution.
this type of research. There are two areas. One is the hydrogen production. Other is the hydrogen storage. And this hydrogen storage actually is for the industrial application. Yeah. And you can you can do the in situ reaction. If the hydrogen is coming, then you can make the another setup to supply that hydrogen that is produced during this reaction for the other reaction.
Because in plants, that is the water splitting through this is based in photosynthesis. You must be knowing that in plants, water is splitting with the help of oxygen and hydrogen evolved. So that oxygen has been utilized. They have been given out by plants. We are getting that oxygen, and the hydrogen is well captured by the plant. That is one specific way the plant has given. So they utilize that hydrogen in many other purposes.
For that, actually, you make the setup in that way.
Yes, sir. Thank you.
So with this, I would like to thank Professor Taqir Ahmed.
Thank you.
And,
thank you all.
Thanks for giving a big applause. So
I request Professor BK Singh to kindly come up on the stage and felicitate our first speaker, Professor Farhan Ahmed, for his insightful talk. Professor Ahmed has to leave because of some prior commitment. Thank you, Professor. Hand over the session to you again, sir.
So thank you. And now we have the third lecture in line, and is going to deliver by Dr. Kuntal Manna. And he is associate professor in Department of Chemistry, IIT Delhi. He has completed his master's degree in 2006 from IIT Kanpur. After that, he went for PhD to Iowa State University and completed in 2012 with Professor Sado. And then he shifted to University of Chicago for the postdoctoral position. And he joined IIT Delhi in 2017 as assistant professor. And here his research is focused on the development of heterogeneous catalysis for sustainable organic transformation, functionalization, and upgradation of light hydrocarbon and energy related transformation. So, with this introduction, I would like to
Thank you.
please, Dr.
Thank you.
Manna.
Thank you for your introduction. And good afternoon, everyone. So before I start, first I want to thank Deshbandhu College, the conference organizer, and Dr. Pratibha for kind invitation. So today I'm going to tell about methane activation. All of you from your high school knowledge, you know that the methane is a odorless and colorless gas. And it is the primary component in natural gas as well as biogas. In our country, methane is used like in use as a fuel, as a compressed natural gas, that is CNG in car, or it is also used for domestic heating as a PNG, piped natural gas. It is also used for electricity generations. But also now methane is turned out to be the second most abundant greenhouse gas in the world. Nowadays, it is accounts about more than 20% of the greenhouse gases. And not only for that, methane's heat capacity, the heat trapping capacity is very high compared to the carbon dioxide, that is 80 times more potent than carbon dioxide. So what is happening is that the methane is released to the atmosphere from various sources. One of the primary sources of methane emission into the atmosphere is the oil and natural gas field, and also from the coal mining. A significant amount of methane is trapped in the coal mining, that is called coal bed methane. If you see any picture, if you go to a oil refinery or oil field, you can see there are chimneys that is burning gases all day, all year, 24 hours a day. So what is happening, that the significant amount of methane which is produced there during the oil refining or oil producing parts, those are the remote, either in the remote location, or it is difficult to trap or transport, and it is not commercially viable. So they are basically being burned and transformed to the carbon dioxide. So we thought that why not we develop a catalyst or catalytic technology that can convert this waste methane to a valuable product, for example, alcohols or acetic acid. So if we just simply heat the methane or natural gas with oxygen or air and convert to something useful. So one of the compound we are interested is in our lab is acetic acid. We know that acetic acid we eat as a vinegar, and also it has a huge industrial applications. It has a global demand of 6.5 million metric ton per year. So in industry, acetic acid is synthesized from methane or natural gas in via three-step process. The first step is the steam reforming of methane that produce the syngas. It is a very high temperature process. Then the syngas is converted to methanol, and then methanol is converted to acetic acid using CO as a toxic reagent and the iridium or rhodium catalyst that you know in your MSc books, like that is a Monsanto acetic acid process or Catibaba process. So why not we just mix the methane and oxygen and directly get the acetic acid selectively? If it is that, then it can solve many issues also in the current processes. And if you develop these transformations using earth abundant metals, using a low temperature, then many issues can be solved in the current process. One of the steps is that one of the advantage will be that it will be the less capital intensive process is the direct transformation. Another steps will be that another advantage will be that it will be if you can do that transformation low temperature, then we can avoid this high temperature syngas process. You can use oxygen, is the cheapest oxidant in the world. And also if you develop this transformation that methane plus oxygen equal to acetic acid using a abundant metal, then we can also avoid these toxic and precious metals. But the transformation methane plus oxygen equal to acetic acid is very challenging, and challenges come from kinetics as well as thermodynamics. The first is the kinetics. The methane CH bond is very strong. It is very difficult to activate. It is CH bond energy is 104 kcal per mole, that we know. Methane is also the CH bond is very non-polar. It is not polarizable also. And another one thermodynamic challenges is that if you want to oxidize methane, then it is very difficult to stop the reactions in the middle product, like methane to methanol, methanol to formaldehyde to formic acid to carbon dioxide. It will go all the way towards the carbon dioxide because it is thermodynamically favorable. So it's difficult to stop in the middle stage. And if the transformation is methane to acetic acid, then there is one more challenge, that is the CC bond formation. So CH activation, methane oxidation, partial oxidation, and the CC bond coupling, everything have to occur together in the same time, similar time to get the acetic acid, otherwise you will not get acetic acid. So in literature, the metal catalyzed CH activation of methane is mainly followed by 4 pathways. One is the standard textbook example is the Silov chemistry, that is mainly done by the platinum catalyst. Second one is the sigma bond metathesis, where methane is activated by a electron deficient metal centers when metal is the D0 system or it is highly electron deficient. Opposite way is that methane can be activated by oxidative addition, is organometallic chemistry. If methyl is highly electron rich, then methane can be activated by oxidative addition. And another one pathway is the O2 addition. You can activate methane by a zirconium amido complex. This is a specific example. So we are interested to develop a catalytic systems using metal organic frameworks for direct conversion of methane to value-added products. Why we are interested in MOF? We are working on MOFs in our lab because MOF is the constructed from metal ion or metal oxo clusters, which are connected by bridging linkers to get 1, 2, or 3D frameworks, which is called MOF. So MOF-based catalysts can provide the advantages of both homogeneous as well as heterogeneous catalysis. The first of all, this is a crystalline material. You can get the structure by single crystal powder, single crystal XRD. If you not get the single crystal structure, then you can reduce the structure from the powder XRD. It is crystalline material. It has a well-defined molecular nature, and not only for that, it has a reticular synthesis. It is isoreticular. Most of the MOFs are isoreticular. That means that you can tune the pore sizes. Porous materials, you can tune the pore sizes, you can decrease or increase the pore sizes, keeping the structure same. Not only for that, it has also the properties of heterogeneous catalysis. MOF-based catalysts are mostly heterogeneous, and we know that it's a heterogeneous catalyst has the advantage of recovery and recycling. And also you can make a very robust catalyst by site isolation within the MOF pores. So our idea is to activate the methane first. First is the methane activation. To develop a single site earth abundant metal hydride, oxo or hydroxo or peroxo complexes at the node of a metal organic framework, where the nodes are composed of high valent metal ions, suppose zirconium 4, hafnium 4, cerium plus 4, because these metal oxo nodes will be highly electron withdrawing. It can create the metal center highly electron deficient, so that methane can be activated via sigma bond metathesis. Not only for that, there are many other advantages of using the MOFs I listed here. So now I am going to tell that the development of a single site copper hydroxyl catalyst using a UIO type MOF, which can directly convert the methane to acetic acid using oxygen as the oxidant. The catalyst synthesis is very simple. It's very straightforward. So basically, if you just heat the solvothermal synthesis, you heat steric ammonium nitrate and benzene dicarboxylic acid in DMF at 100 degrees centigrade. Within 1 hour, you will get a very crystalline material of UIO type MOF using the cerium SBUs. So if we just zoom in these secondary building units, you can see this. This is the secondary building units. It is composed of cerium plus 4 ions, oxo and hydroxo, and this is the bridging units. And there is a mu3 hydroxyl groups are there which can be used for further catalyst development. So next step, what we did, we treated with a base N-butyl lithium at room temperature in THF to deprotonate these hydroxyl groups, then simply metallations by salt metathesis route by treating with copper dichloride to give this MOF node supported single site copper chloride species. And next we treated with sodium triethyl borohydride. So this sodium triethyl borohydride, what it does, it just convert this copper chloride to copper hydride, and then we added water to get this copper hydroxyl species. So not all hydroxyl species are metallated with copper hydroxyls. So ICPOES tells that about 45% OH group is metallated with copper. So this is the characterization. So the structure of the MOF is characterized by powder XRD. This is the simulated powder XRD from the UIO MOFs. We can see the similarity of the powder XRD pattern of the pristine MOFs and the metallated MOFs. It indicates that the MOF structure is remain same. It is crystalline and it has a UIO structure also. The MOF is also, the MOF catalyst is also have high surface area. It is highly porous. So before metallation, it has around 800 meters square per gram, and after metallation, because of the incorporations of the copper hydroxyl groups, it has the surface area decreased as expected to 570 meters square per gram. The oxidation state of metal center was determined by XPS, that is the surface techniques, and the ZENS, which is the bulk analysis. So both the ZENS is the, okay, in MSc students, if you don't know, it is the X-ray absorption spectroscopy. So in ZENS, this is the beginning, this is the beginning part, this is the KH of the copper. It also indicates that ZENS, this is indicates, and XPS also both indicates that copper is +2 oxidation state in the MOF supported copper hydroxyl catalyst. What is the coordination environment of copper ions? So that is only one technique we have used, and that is reliable, that is the XFs. So the XFs fitting with the DFT optimized structure indicates that copper is di-coordinated. This copper is coordinated with mu, this now it is mu4 hydroxyl groups, hydroxyl, and it is surrounded by carboxylate oxygen. The XFs analysis also tells that there is the absence of copper scattering. If you compare the other copper standards like copper dihydroxide or copper cupric oxide, then there is no copper scatterings. So that indicates that whatever the species we have, that is a monomeric isolated copper hydroxyl species, and there is no neighboring coppers. There is no copper nanoparticle. If you also see the XFs with the copper foil, that is a metallic copper foils, and we also fitted these XFs with 2%, 1%, 5% copper nanoparticles, and we found in this MOF catalyst there is no copper, metallic copper present. So this MOF supported copper hydroxyl material we used for direct oxidation of methane to acetic acid formations using oxygen as the oxidant. We used a high pressure batch reactor, oxygen is the oxidant, we used water as a solvent, and the liquid product, whatever we get, that we analyzed by HPLC as well as GC FID, and the gaseous product we analyzed by GCTCD. So this is the optimization. So we can see that the yield of acetic acid increases with temperature, and the maximum yield is obtained at 115 degrees centigrade. Beyond 115 degrees centigrade, the product of the yield of acetic acid decreases significantly. That is because mob degrade at high temperature. That is one of the defect of this material. And not only for that, at high temperature also acetic acid, what is a product, is also degrading to the methane and carbon dioxide. So we also varies the time. So at 40 hour we got the optimum yield. Beyond 40 hours we have to stop the reactions at 40 hours, this methane oxidation reactions. Beyond 40 hours the acetic acid also further converted to the carbon dioxide. Oxygen pressure and methane pressure is also important. The yield of acetic acid depends on the oxygen pressure. At 6 bar of oxygens we get the highest acetic acid yield, and also it depends on the methane pressure. I will explain later the why. So at 30 bar of methane we also got the highest amount of acetic acid. So in the optimized conditions, what we got, that we started with methane 30 bar, that is a 42 millimole of methane. Oxygen is 6 bar, and we got acetic acid 1.24 millimole with negligible amount of carbon dioxide and CO. So that is terms into like 6% conversions and more than 98% selectivity. That is the highest selectivity among any other catalyst reported in literature. So we did a lot of control experiments. So first of all, if you do the oxidation reactions in absence of catalyst, there is no conversion. So that indicates that for methane to acetic acid, we need the catalyst. If you do the catalysis in absence of methane in the entry number 3, then no product. That indicates that whatever the carbon source in the acetic acid, that is actually coming from the methane, not from any other else, not from the material. Also, if we do the catalysis in absence of oxygen, there is no catalysis occurring. And also another one interesting thing is that if we use CO, carbon monoxide, instead of methane, the entry number 6, then we also didn't get the acetic acid. But instead of this, we got small amount of methanol also. We also did a lot of control experiments. For example, we check the catalytic activity of copper dihydroxide, cupric oxide, or cupric oxide entrapped within the cerium UiO MOF, or cerium oxide supported copper hydroxides. None of them are catalytically active. So we got the very good activity for the cerium UiO copper hydroxyl catalyzed reactions. So next we analyze what is the mechanism. So first of all, we found that if we do the reaction in presence of CO, then reaction occurs. Also, not only for that, we also found a small amount of CO is always producing in the reactions mixtures. If you do the catalysis in the identical reaction conditions of the optimized conditions, there is no catalyst, but if you just heat it, the methane and oxygen, we got the CO. And not only for that, that if you do the methane and CO, we get the acetic acid, there's no oxygen. So this indicates that most likely in the optimized reaction condition, some amount of CO is producing by the reaction of methane and oxygen, and that might be the CO is a reactive intermediate. We also catalyze the MOF species after catalysis, and we found that even after the catalysis, the structure is remain same. The copper is +2 oxidation state based on the XPS, and this is the Zen spectra. And the resting state, that is the copper species that we get after recovery of the catalysis. After the catalysis, what are the species we get? That is the called resting state. And in the XFS analysis, we found that the structure of the species is the copper hydroxyl species. So based on this experimental data, we propose that the first step is the methane activation, where methane is activated with copper hydroxyl via sigma bond metathesis to get the copper methyl species. Then CO coordinate, and CO is formed by the oxidation of the methane and oxygen, that is in situ formation of CO. That CO is coordinated to the copper to give this species, and then the insertion of the CO with the copper methyl species to give this intermediate 3, and then the hydrolysis with water to gives the copper hydride and acetic acid product, and then hydride reacts with water to give the copper hydroxyl species. And this is the balanced chemical equation. The 2 methane molecule with 1 molecule of water and half molecule of oxygen gives the acetic acid, and hydrogen we also detect, we also quantified the hydrogen by GC. We also calculated the whole catalytic cycle by DFT to understand what is the turnover limiting step or rate determining step, and we have found that the first step, that is the sigma bond metathesis between the methane CH bond and copper hydroxyl groups, is that have the highest barrier and turnover limiting step. So the project is still going on, and we recently have developed another one, iron catalyst, whose activity is much higher than this catalyst. It is not published yet. So for that, I want to thank my students. This is the past and present student. I didn't do any reactions, by the way. So all are done by my students. This project was done mainly by the first three students, Neha and Till, who graduated last year and now a postdoc in Max Planck in Germany. And Manav is the fourth year students. I want to thank all the funding agencies, GAIL, ACRB, CRG project, RRCAT for XFs, CSIR for students funding. And finally, I want to thank IIT Delhi for funding and support. Thank you. Questions?
So, thank you, Dr. Manna. If there is
Thank you. Very interesting lectures and done the
Thank you.
very good work. Just I want to know that you have just made this cerium MOF, then you have added this copper.
Yeah.
And in that step, you have used this N-butyl lithium. Okay. So it is, you have to check this reaction without N-butyl lithium, reaction is not happening. And but you have to, it is necessary to take the N-butyl lithium because already hydroxyl group is already there. But there is copper one you are taking. So without N-butyl lithium, reaction will not happen.
What happened? I think let me tell. Yeah, this slide, right?
Yes.
Yeah. So what is this?
No, after that, this
This is the characterization step.
no, before that. So just for the cerium MOF, you have just taken the copper one.
Yeah.
And that step you are using the N-butyl lithium.
N-butyl.
Just I want to know without N-butyl lithium is happening or not. That's why I want to know.
N-butyl lithium is?
Without N-butyl lithium.
No, this will not happen. This will not happen.
Okay.
No.
What is the temperature you are taking for that?
It's a room temperature.
Room temperature.
If we add without N-butyl lithium, if we just add salt, little bit will absorb. Then you can wash away. But without N-butyl lithium, these reactions or the grafting of the metal ion will not happen. You need a base, and we used N-butyl lithium in THF at room temperature.
Okay.
Yeah, thank you very much for this very nice talk, sir.
Thank you.
So in your mechanism, you are saying that CO2 is in situ generated.
Yeah.
And that is helping in the insertion of CS3 bond. Yeah. So it is possible that along with this, carbon dioxide is also produced, and that will also help in a, it's like the way CO2 is doing, the CO2 may be produced, and that will help also help
CO2, if you add CO2, okay, no reaction happens. But if you do CO, reaction happens.
So CO2 is
CO2 is also producing small amount, definitely, because if you have methane and oxygen, and CO2 is more thermodynamically favorable. But CO2 doesn't take part for this. And CO2 is the +4 oxidation state. It's already down. You cannot go back to acetic acid. This is oxidation reaction. You have to reduce it. CO2, you have to reduce it. Yeah. Okay. You understand my point? Yeah.
Thank you very much.
Yeah. Okay. Yeah.
Very nice talk, sir.
Thank you.
Sir, I just want to ask, like, there are many bacteria also, which this process is produced, like acetic acid.
Yeah.
So
methanol also.
Methanol and
yeah.
So the production of this acetic acid, did you quantify, like if we use bacteria and then we isolate the bacteria, what is the amount of acetic acid produced as compared with the chemical process? Because which process would be more economically favorable? Like
this is all depends. Okay, and what's the scale you are doing? Like in ethanol
like
production,
in recombinant
you are
technology.
doing a fermentation process versus
yes, fermentation.
like methane is okay. But if you do something like bacteria, then you have to do like what is the bacteria cost, what is the scale, how fast it is. Okay, because any fermentation process or other, this is the slow process also. Okay,
Achha.
What scale you will do, and not only for that, idea is that you can develop a catalytic systems in the remote location. So a lot of that I told in the introduction slide, that the methane is producing suppose in remote locations in an island, okay, it's very, very difficult to trap. Okay, so there you set up with a, like in bacteria, it is a very fancy method, so it will be difficult.
We
So
can isolate the bacteria and then we can grow the bacteria
it
in
all
large
depends on
amount.
the engineering also. Okay, that what scale you will do and how fast it is. Even for our current system, this is only giving 6% conversion. So I will not tell it is the we are going to commercialize.
Only 6%.
Only 6%. But it is almost 100% selectivity, 99% selectivity. So we are still working.
Means most of it would be acetic acid.
Is that 99% is
99%
acetic acid?
acetic
Yeah,
acid.
acetic acid. And actually, one of the issues for here is the catalyst stability. If you do longer reaction time, and like we can recycle 3-4 times, but after that catalyst degrade, the mob degrade. And not only for that, if it's high temperature, it also slowly degrade. So we have to fix this issue, and we are doing this reaction in a batch reactor. But if you do in a flow reactor, I'm 100% sure that we will get the much better activity, but we don't have the setup.
Okay.
Flow
and,
reactions.
And
Okay.
can you use palladium also? PD?
Palladium. Oh, forget about palladium. We don't have money to purchase palladium.
Achha.
I don't care palladium because it is a precious metal.
Achha.
Okay. Forget about palladium. I don't care. It's precious metal.
So is there any other question? If no, then give him a big applause.
Thank you. Thank you.
Thank you.
Thank you very much to all the speakers. Now I kindly request our chairperson, Professor B.K. Singh, to come up here on the stage and felicitate our second speaker of the day. And yes, Professor Ramendra as well. To kindly felicitate our second speaker of the day, Professor Tokir Ahmad. Thank you, sir. Thank you for the really interesting talk. Now I would like to invite Dr. Kuntal Manan. I request the chairpersons to felicitate him as well. Thank you, Dr. Manan. Thank you so much. Thank you, sir. Thank you. Now I request Dr. Umesh Kumar to kindly come up on the stage and felicitate our chairpersons. First of all, I would request Professor B.K. Singh to kindly come up on the stage and receive our small token of appreciation. Thank you very much, sir, for patiently handling the entire session. Now I request Professor Ramendra Pratap to kindly come up on the stage and receive our small token of appreciation in the form of a memento. Thank you so much, sir. Thank you. Thank you, sir. Thank you, Umesh, sir. I thank the entire audience for the patient listening. And we will now break for tea. And in 20 minutes, we will resume the conference proceedings with the next session. So tea will be served in the multipurpose hall. Kindly partake of it. Thank you. See you again.